exponential form of complex numbers, which we're really doing now because we're going to need this a little bit later on. So we have this new identity, Euler's identity, which is e to the I theta is cos plus I sine theta. Using this, it's possible to write trig functions in terms of complex exponential functions, functions involving e to the power of a complex number. And what's interesting is that all of the properties of trig functions we've ever met can then be derived from that. And when I do this, you will think, hang on, this reminds me of something else. So e to the I theta is cos theta plus I sine theta. If you replace theta with minus theta on both sides, you get e to the I theta is equal to, so e to the minus I theta is equal to cos of minus I theta plus I sine of minus theta. Now, two little properties of trig functions that will arise every now and again are these. The cos of a negative is the same as the cos of a positive angle. That's because the cos graph is symmetrical about the y-axis. The sine of a negative angle is the negative of the sine of an angle. So consequently, this can be written as cos theta minus I sine theta. So we've got these two expressions. We've got e to the I theta is cos plus I sine. Whoops, I wanted to change my pen. We've also got e to the we've got e to the minus I theta is cos plus minus I sine. Now, if you add these two equations together, you get e to the I theta plus e to the minus I theta is 2 cos theta. And then divide by 2, you get cos theta is e to the I theta plus e to the minus I theta, which is supposed to look a bit familiar. If you subtract these two equations, the cos thetas will cancel out. You get e to the I theta, take away e to the minus I theta on the left. Cos take away cos is nothing. I sine take away minus I sine is 2 I sine theta. So consequently, sine theta is e to the I theta, take away e to the minus I theta over 2I. Now, guys, what you're supposed to realize is this looks a lot like the definitions of cosh and shine, and this is really where the definitions of cosh and shine come from. If you take these two expressions and literally cross out the i's, the expression for cos turns into cosh, and the expression for sine turns into shine. But you can view this as ways of writing trig functions, cos and sine, in terms of complex exponentials. And conceivably, we may have problems which we can solve using these. So I'm going to use these to prove two things. The first of which is just nice. I'm going to prove one of our standard trig identities from using these identities. And then the second one is more illustrative of something we might possibly need at a later stage. So it says use the expressions above so that sine squared theta plus cos squared theta is always equal to 1. So what I know is that sine squared theta plus cos squared theta, by the way, this is going to feel very much like how we prove hyperbolic identities, is e to the I theta minus e to the minus I theta all over 2I squared. That's what my sine theta is. Add my cos theta is e to the I theta plus e to the minus I theta over 2 squared. And now I'm going to square the tops and bottoms of these. So the first one, if you square the bottom, 2I squared is 2I times 2I, which is 4I squared. I squared is minus 1, so we get minus 4. If you expand the top, e to the I theta take away e to the minus I theta times another bracket. Well, e to the I theta times e to the I theta is e to the 2I theta. Adding the powers together. E to the I theta multiplied by minus e to the minus I theta, add the powers and you get 0. So that gives you -1. If you do it the other way around, you get another -1. So that's -2. And then minus e to the I theta multiplied by itself. Minus times a minus is a plus. Adding the powers together, you get -2I theta. Squaring cos is similar. So squaring the bottom, we just get 4. Squaring the tops, we get e to the 2I theta. We get +2, that's e to the I theta times e to the minus I theta, which is e to the 0, and the other way round. And we get to e to the power of -2I theta. Then, in order to add these together, I think what I'm tempted to do is just reverse all the signs in the first fraction. So times top and bottom of the first fraction by -1 to end up with a +4 in it, and then we can add the tops. So that's going to give me minus e to the 2I theta plus 2 minus e to the -2I theta, all divided by 4. And then for my second fraction, e to the 2I theta plus 2 plus e to the -2I theta, all divided by 4. Now, if you add the tops together, that minus that and that cancel out. 2 plus 2 is equal to 4. And then that and that cancel out. So we just get 4 on top, and 4 over 4 is equal to 1. Now, the final example I'm going to prove to you is an example of the kind of thing that we may require in certain aspects of in a certain type of problem that's going to arise at a later stage in this course. I want to show that 1 minus e to the 2I theta squared is equal to 1 minus 4e to the 2I theta times sine squared theta. So what I'm going to do is start with the left-hand side and simplify it as much as possible. And then I'm going to do the right-hand side and simplify that and hopefully end up with the same thing. So if you expand the bracket on the left-hand side, you will get 1 minus 2e to the 2I theta plus e to the 4I theta. And then I'm going to leave that there. If I now type the right-hand side, I get minus 4e to the 2I theta multiplied by sine squared theta. And sine squared theta is e to the I theta, take away e to the minus I theta over 2I squared. That's minus 4e to the 2I theta into, now we've already squared this out actually. On the bottom, 2I all squared is minus 4. And then if you expand e to the I theta, take away e to the minus I theta squared, you will get e to the 2I theta minus 2 plus e to the minus 2I theta. Now what we can do now is we can cancel out the minus 4s. So that gives me e to the 2I theta into e to the 2I theta minus 2 plus e to the minus 2I theta. Expand the brackets and you get e to the 4I theta minus 2e to the 2I theta plus, if you multiply the last term together, you get, adding the powers, you get 0, and e to the 0 is just 1. And that is 1 minus 2e to the 2I theta plus e to the 4I theta. So that proves that the right-hand side is equal to the left-hand side. So consequently, that proves the thing I was trying to prove. So therefore, 1 minus e to the 2I theta squared is minus 4e to the 2I theta times sine squared theta. That's what's required. Okay, folks, you may now have a go at exercise 1B.